In the topic radiation sources, we will discuss cyclotron produced radionuclides and production of radioisotopes. Most of the radionuclides used in nuclear medicine are artificially produced. There are about 2,500 artificial radionuclides as on date, produced by variety of methods. Most of them are produced by cyclotrons or nuclear reactors or radionuclide generators. First, we will discuss the cyclotron produced radionuclides. As we know, cyclotron is an accelerator. This cyclotron accelerates or cyclotron accelerators produce radionuclides by bombarding stable nuclei with high energy particles. Protons, neutrons, and alpha particles are commonly used to produce radionuclides. Best example is gallium-67. The production reaction you can write as gallium is produced from zinc 68 by bombarding the zinc 68 with a proton, and you will be getting gallium 67 plus 2 neutrons, where Zn68 is the target and proton, which is accelerated to about 20 MeV, is the bombarding particle. During this reaction, 2 neutrons are also emitted. In some cases, the nuclear reaction produces radionuclides that decays and gives newer radionuclides. For example, if this is the product one by the bombarding particles, this will decay to give new products, and that products we are using. Examples are iodine 125, iodine 123, and TL20. And the next method is nuclear reactor produced radionuclides. Neutrons, being uncharged particles, have an advantage of penetrating through the nucleus without being accelerated to high energies. The nuclear reactor uses 2 methods to produce radionuclides as given below, and they are nuclear fission or neutron activation. We will discuss them one by one. First, nuclear fission. If neutron bombards with the high atomic number nuclei, the nucleus splits into nuclei of lower atomic number with additional neutrons. This is known as fission process. We have not got an example here. This is known to us. The fission of uranium, thorium, etc. are known to us. The radionuclides obtained from the fission process are mainly molybdenum 99, iodine 131, and xenon 133. These are separated from other fission products. They are said to be carrier-free since no stable isotope is present. That is a term carrier-free because this type is normally naturally not occurring, but we are producing it. Hence, their specific activity is higher, which is very much required for radiopharmaceutical preparations. And our second method, neutron activation. Nuclear reactors with uranium fission produce neutrons, which can be used to create radionuclides by bombarding stable target material placed in the reactor. Reactors are provided with ports between the fuel elements to place sample material which is to be irradiated. The sample material captures neutron and the process is called neutron activation. So, you are placing some material and they are transferred to other materials by the absorption of neutron. So, they are activated to other materials. That is why it is known as neutron activation. Radioisotope of an element is prepared by placing small quantities of pure element in small containers made of aluminium in the port of an atomic reactor for a period of several weeks. The element is converted into radioactive isotope due to continuous bombardment by neutrons inside the reactor. For example, cobalt-60 is produced with the N-gamma reaction. N-gamma means this N is the bombarding particle and this gamma is the particle which is produced. So, this is the reaction. Cobalt-2759 gives neutron plus neutron will give you cobalt-2760 plus gamma. And as we know, this cobalt-60 is much used radioactive element. The N-gamma is a most common neutron capture reaction for thermal neutrons. As we know, the term thermal neutrons means neutrons which have energy corresponds to our room temperature or very low energy neutrons. In this, the gamma follows immediately after neutron capture. That means neutron capture, gamma is produced. However, there are other neutron capture reactions, namely NP. That means when neutron is bombarded, proton is produced. And N-alpha, N and alpha. In this, the emission is P and alpha respectively. Other examples of radionuclide produced by the method of neutron activation are phosphorus 32 and krypton 51. The main one is, as we have discussed, it is cobalt-60. Usually, all radionuclides produced by neutron activation decay by beta minus particle emission. We are familiar with the beta emission of cobalt-60. So, all these produced radionuclides, they are also active, radioactive one. So, they will normally decay by beta minus particle emission. And that's all in this small lecture. Thank you.